In this video, we'll go through some questions involving the power rule. And then in the next one, we'll go through some questions involving the chain rule. But we'll keep using these two rules as we go through the different applications, right? The whole part of applications of differentiation. Remember, we're going to apply these two rules to about 6 different concepts, okay? Of which some we'll see them right now as we are doing this basic version of application of these rules, okay? The power rule is the more prominent one because we're going to use the power rule in about 4 or 5 of the 6 applications. We'll really use the chain rule in connected rates of change. That's where we'll really apply it. And then the rest will just be applying the power rule. We'll see, and it'll get more obvious as you see questions. Okay, now quick recap though, as before we go through the questions of this power rule. Remember that we did about 3 versions of the power rule. The first one was the basic one where we just had x to the power of something, right? And n, we have here x to the power of n. Remember that n is just going to be a number, right? X to the power of n, we know that n is going to be a number. How do you do the power rule? You bring down the power, then you reduce the power by 1. That's easy. So it's going to be nx to the power of n minus 1. So the power of x goes down by 1. You bring down the power first, then you reduce the power by 1. If you had a number in front, okay, then your answer is going to be the multiplication of that number and the power. So you bring down the power and it multiplies the number. Then the power reduces by 1. Okay, that's just a shortcut. Remember that we bring down the power, it multiplies the coefficient, which is the number in front of x, which is a in this case. So you get an, then you reduce the power by 1. And then the last one, in simple terms, here we have, remember that we just have it, the 3 parts of this number are adding or subtracting. In this case, they're doing both, right? At one position, there's an addition sign. Here, there's a subtraction sign. And we said when we have a scenario like that, we differentiate one part at a time. That's what this rule is just saying here when you have the derivative of ax to the n and then bx to the m and then cx. We are differentiating one at a time, and we put that sign in front. We never ignore its sign, the sign that it had, okay? And we were going to differentiate it. Although we don't need to put this d dx in actual calculations, but here we're just communicating to you that you're going to differentiate each part. So don't forget that. Let's go through questions. First one is saying, find the derivative of each of the following with respect to x. Okay, so it's going to be dx in the bottom there with respect to x. All right, so I'm going to say in first d dx of x to the power of 5. Why do I say d dx? Because x to the power of 5 is an expression. It doesn't have an equal sign. It is not it's not written as a complete function. It's just an expression. So I can't say dy dx or d something dx. It's just d dx of x to the power of 5 is going to be, remember, this is the most basic version. I just bring down the power, so it's going to be 5. Then x is now to the power of 5 minus 1, which is 4. Done. Now, the next one, 1 over x cubed. I must find the derivative. Now, to find derivatives, you cannot have your original expression as a function, as a fraction rather, if you want to use the power rule. If you want to use the power rule, then you're going to need to have it, have the fraction dissolved, okay? And we know that 1 over x cubed is the same as x to the negative 3. So that's going to be like the first line I'm going to do, right? We're going to say, now we are answering, 1 over x cubed is equal to x to the negative 3, okay? I don't have space, so I'm writing in the same line, okay? But you'll be writing here at the bottom below that, and you'll be answering. So 1 over x cubed is equal to x to the negative 3, right? And then when I have it like this, I'm now able to use the power rule. So when you go to P3 and we learn more, you're going to learn about what is called the quotient rule, which is going to have a fraction, okay? But you don't need to actually break that fraction. But in the cases of quotient rule, most of the times you won't be having a number as your numerator. Okay? I'm saying this for people that are going to write both P1 and P3 at the same time. You're not going to have a number on your numerator. This one, when we have a number and our x is in the denominator, we're going to need to take the x out of there. And that is why we learned those things in prerequisite knowledge. It's so that you can apply it right now. Okay? These indices. So 1 over x cubed is equal to x to the negative 3. And now I can find d dx of x to the negative 3. It is now equal to, remember I'll be writing going down. What is it equal to? You bring down the power, it's going to be negative 3. Then you reduce the power by 1. So it will be x to the negative 3 minus 1, which is going to be negative 3 x to the negative 4. That is the final solution. We go to number 3. F of x is equal to the cube root of x. Now here we have it written as a function. And when we're going to find the derivative, we write it in Lagrange's notation or in functional notation, where we say the derivative f dash x. Remember that your dash is forward leaning. It's like it wants to fall forward. It is before we get the derivative, because we have it with the cube root, we're going to have to get rid of that cube root sign first. So, you would have to then say f of x is equal to x to the power of 1 over 3. I'm sure you know this from prerequisite knowledge. If you don't, I recommend you to go watch prerequisite knowledge, which is going to be covering indices. It was covering indices, so you just go what you see. Okay? Because remember we said the root, when we change it to a power, the root is going to be the denominator. The denominator is the root, and then the numerator will be the power. So this is the numerator. And since this x did not have a power, it only had a root, that means its numerator was a 1. So that's why we put it as f of x is equal to x to the 1/3. Now f dash x will now be equal to, we can now get the derivative, okay? Maybe I could write it below there to say f dash x is now equal to, I bring down the power, it's 1/3, x to the 1/3 minus 1. Okay? And I'm going to get it as f dash x, the first derivative is going to be 1/3 x to the negative 2/3. I'm done. Now I go to number 4. I have 5x, and I'm supposed to find the derivative. Okay? So I'll just say d dx, the derivative of 5x is going to be equal to, now this is the easiest one. Whenever you differentiate something that only has an x, it's not x to the power of something, it's just an x. When you differentiate it, you just get the number, so it's going to be 5. Okay? The derivative of negative 3x is just negative 3. The x just disappears. Okay? Because in here you would say x is like saying x to the power of 1. So if I'm to use the chain rule, I'll say 1 times 5, I get 5. Then x is now to the power of 1 minus 1, which is 0. So x goes. Then the derivative of a number, d dx of a number of 7, is just 0. The derivative of any constant, any number, is 0. So we are done. This is going to be the first 5 examples. Let's look at the next one now. This one is the more, is nice actually, but it's the more advanced version rather. It's the more advanced version of what we're seeing, because now we have them as different situations in one. So remember that the first thing we're going to have is rewrite this whole thing, breaking down the fractions and removing these square root signs. Okay? Whenever you want to differentiate using your power rule, because we're going to use the power rule here, it falls in the third situation of power rule, where things are just adding and subtracting each other. So we're going to have to express everything as powers. Whether they are negative or positive, we don't matter. It doesn't matter to us. Okay, so let's go ahead and do that. 4x cubed is still going to be 4x cubed. Negative minus 1 over 2x squared is going to be half, because we bring down, we take away the number, okay? So it's going to be half, because 2 is in the denominator there, so it's still in the denominator, half. And then x is now to the negative 2, because x was squared. When we put him out of the denominator, is now to the negative 2. Plus, we have 3, because it was a 3 on the top. If it was 3 at the bottom, it would be 1 over 3. But because it's just a 3 at the top, it's 3. Then what about x? X in this denominator is going to be 3 over x to the power of half, because this is square root. So we could first put that, okay? We would say plus 3 over x to the power of half, because we know that root x is x to the power of half. Then we say plus 5. Then we go ahead, we can simplify it again. It's going to be 4x cubed, then minus half x to the negative 2. Then plus 3 is now multiplying x to the half, but the half was in the denominator. When it goes up, it's going to be x to the negative half. And then plus 5. Okay? Now we can now write to say d dx, because we have changed its form, we can now say d dx of 4x cubed minus half x to the negative 2 plus 3x to the negative half plus 5. What is this going to be equal to? We can now start to find the solutions. In here, we'll say the power times the coefficient. So 3 times 4 is going to be 12. X to the 3 minus 1 is 2. Then we have negative 2 times negative half. Now here we're about to do more on directed numbers. I would recommend you check what I said about directed numbers. Okay? I have a video on that. You can check on the site. You just search directed numbers. You just say negative 2 divided by negative half. Whenever you are multiplying two negative things, or I might as well tell you right now, it's nothing really. When you, for division or multiplication, either one of the two or even both of them, when you multiply negative by negative, for example, you will always get a positive answer. Or when you multiply positive number by positive, you also always get a positive number. This is true for division or multiplication, because if I say negative divided by negative, I will get positive. And if I say positive divided by positive, I will also get positive. But if I say negative times positive, then my answer is going to be negative. If I say positive times negative, then my answer would be negative again. If I say positive divided by negative, then I'm going to get negative. Okay, let me be writing with you. Okay, let me be writing. Then here I'm going to get negative. I'm not making you cram. I'm going to explain why that is happening. Here I'm going to get negative. And finally, if I say negative divided by positive, I will get negative again. Why? Why is that so? Because whenever you divide, look at this. The answers that were giving me, the guys that were giving me positive answers, what do you see in common? It is that we are multiplying two things that have the same sign. If I say negative times negative, I will get positive. Do you know why? Because the two things have the same sign. Positive times positive, they have the same sign, so they're going to give me a positive answer. This is for division and multiplication. Negative divided by negative, they have the same sign, so they're going to give me a positive answer. Positive divided by positive, they have the same sign, so they will also give me a positive answer. But when I multiply two things that have different signs, my answer will always be negative. If I say negative times positive, the signs are different here, so my answer will be negative, straight. If I say positive times negative, the signs are different again, my answer would be negative. So just make sure you know when you divide and multiply things that have different signs, your answer will always be negative. No negotiations, nothing will change. Okay, so I'm going to say, and it'll be equal to, I'm now going to say, here I said we multiply the power by the coefficient. Negative 2, remember it's a negative number because it has a negative sign in front of it. By negative half, it's another negative number, there's a negative sign in front of it. Okay, it's going to give me positive because the signs are the same. Then I'll just say half by 2 if you want to put it step by step, right? Half by 2. And then x is now to the power of negative 2 minus 1. Okay, I'm doing the longer way. Then here is going to be plus, what do we have? Negative half times 3. So your answer is negative because the signs are different. And then you would have 3 times half. Okay, we are now ignoring the negative. We've used the negative to know the sign. Then x is now to the power of negative half minus 1. Okay, and then now we will have this 5. When you differentiate 5, you always get a 0, of course. Here is going to be 12x squared plus half times 2. The 2 and the 2 will come to remain with 1. 1x, so it's going to be x to the negative 2 minus 1. You get negative 3. You can put it in the calculator if you're not sure. Then minus 3 by half is going to be 3 over 2. Because 3, a whole number multiplies the top. When you multiply whole number and fraction, the whole number multiplies the top. So it's going to be 3 by 1 is 3 over 2. And then x is going to be to the negative half minus 1. So we now have x going to be to the negative 3 over 2. And this would be your final solution. Questions? No questions. That's the derivative. You get your marks. Last two questions. Find the gradient. This is a bit more practical, okay? But we're still using the power rule. We've been using the power rule for all these things. Find the gradient of the tangent. Oh, to the curve. Oh, thank you. The moment you say gradient of tangent to the curve or a gradient of a curve, we have to differentiate. Because differentiation is the one that gives us the gradient of curves at a particular point. If you're not sure again about this, I recommend you go and watch the intro. Okay? So I also covered that. So here we have that we know that by now that we can find the gradient if we know the point. The gradient of a curve, knowing where we are talking about, because the gradient of a curve changes all the time. So you have to tell us your location. Then we can be able to tell you the gradient. Okay? So find the gradient of the tangent to the curve, whatever. So here, what we are going to need is to differentiate, because we are finding the gradient of a curve. Okay? The gradient of a tangent to a curve. It's the same thing as just saying the gradient of the curve at a certain point. Because to find the gradient, you have to calculate the tangent and stuff. But here we are going to be using the method of differentiation. So what do we have? What is our original curve? It's going to say y is equal to x multiplying 3x minus 2, and then multiplying x plus 1. So first thing we do is we are going to have to differentiate. And to differentiate, we have to expand. Okay? So if I'm to expand, I would say y is equal to x is still outside, but I let these two brackets multiply each other. And when I multiply these two brackets, I start by 3x is going to multiply x plus 1. Then I take minus 2 is going to multiply x plus 1. Okay, something like that. And then x plus 1, I can change. Oh, and now when it's like this, then it's going to be equal to y is equal to x is still outside. 3x times x becomes 3 of x squared. 3x plus times 1 is going to be plus 3x. And then negative 2 times x, the signs are different. Your answer will be negative 2, okay, to be negative 2x. Then negative 2 plus 1, negative 2 times 1 rather is going to be negative 2, okay? Then we're going to have y being equal to x, 3x squared plus 3x minus 2x is going to be plus x, and then minus 2. Then now we are going to expand to say y is equal to x times 3x squared is going to be 3x cubed plus x times x is x squared minus 3x squared plus x 3x cubed plus x squared minus 2x rather. Sorry, what's going on here? Minus 2 by x is 2x. And we are done finding our y. Now obviously we can find the derivative. We can now say that dy dx will just be 3 by 3, 9x to the 2, plus the power just comes down 2x to the whatever. So, okay, and then now it's going to be 2x to the 1, and then it's going to be minus 2x will just become minus 2. We've talked about it. Now that we have our dy dx like that, they want the gradient. They've told us. Let's see. Oh, find the gradient at this point, at point 2, 4. So now that's all you're left with. You have the gradient function now. Dy dx we said is the gradient function, which means you are going to be putting where you are, it will tell you the gradient. So we can now say at 2, 4. Is it 2, 4? Okay, at 2, 4, you say comma. X will be equal to 2. Okay? So what it means is that you're going to now say that dy dx, okay, you can now say when x is equal to 2, then we'll be saying dy dx will be equal to 9 by 2 squared plus 2 by 2 by 2x rather. Okay, 2 by x, so which is, what is x? X is just 2, so 2 by 2, yeah, it's fine. 2 by 2 and then minus 2, so it's going to be dy dx will be equal to 9, 4, so 9 by 4, and then here is going to be plus 2 by 2 is now the 4, and then minus 2, so 9y over
is going to get a times 4 is 4a. Sorry, 9 rather. It's 36 plus 4 minus 2, which is 36 plus 4 is 40 minus 2. We can say that dy dx, where can I write that? Dy dx is equal to 38.
Done. Last question, okay? Or we'll do the last question in the next video. Bye for now.